So far in 229, we have studied the execution of code and look at the assembly programming, always with the idea that there is a single processor in my system. There is only one RISC-V processor, and the RISC-V processor is executing the instructions in the sequence in which we wrote those instructions. What happens if there is more than one processor in the system and we need to coordinate the operation of these multiple processors? This is the topic of this lecture. It's called synchronization. And to illustrate the issue with synchronization, I have created an analogy for you that I want to walk you through. And this analogy works as follows. Let's suppose that I have a road and somewhere, and this road there is an error in the road, perhaps due to construction or some other issue, and therefore only one car can pass through that narrow part of the road at a time. So let's suppose that I have Larissa has her truck here, and Larissa is driving along the road and is about to pass the narrow stretch of the road. And here I have Brandon coming in his little car, and Brandon also is about to get to that stretch of the road. Without any synchronization between them, what is likely to happen is that both of them will try to pass into the narrow stretch of the road, and they are not going to be able to pass because one will be blocking the other. So that is not a desirable situation. So let's see if we can fix the situation so that this collision does not happen. So what we're going to do, we're going to improve this part of the road by creating a semaphore. So the semaphore will indicate to me whether this narrow passage in the road is free so that you can pass through, or whether it's occupied or reserved for someone else. So now that we have the semaphore, let's see if we can use the semaphore to prevent the collision into the narrow passage of the road. So the first thing that we'll do is, when Larissa arrives with her truck at this point, before going to the narrow part of the road, Larissa will check to see whether the semaphore indicates that the passage is free. And she's gonna get a response from her reading of the semaphore saying that the road is empty. When Brandon arrives at this point, Brandon will do the same thing. We'll check to see if the narrow passage of the road is free, and we'll receive a message that yes, the road is empty. Of course, Larissa wants to be careful. Larissa wants to make sure that nobody else will gonna pass on the narrow passage of the road when she's passing. So when she receives the message that the road is free, she's gonna change the semaphore to say that it's now occupied because she's about to pass. Of course, Brandon is also careful, so Brandon will also, upon seeing that the road is free, will change the semaphore to make sure that the semaphore indicates to everybody that the road is now busy. So both of them have done the right thing, and both of them are certain that the road is now empty. So both of them will try to pass into the narrow passage, and we again have the collision. So we have not solved the problem yet. So what we have to do to solve this synchronization problem? We need better synchronization. And this better synchronization will consist of a different protocol to use this semaphore. This protocol will be as follows. We have the semaphore as before, and Larissa will send a message to the semaphore saying, I am about to cross the road, and I want to know whether the road is free. So that we'll call it a load reserved instead of a single load. And Larissa will receive a response saying, yes, the road is empty. And so Larissa knows internally now, I made a read of the semaphore. The semaphore has told me that the road is empty, but my read was not a normal read. My read was a load reserve read. Brandon at the same time will do the same thing. Brenda will read the value of the semaphore, again using a load reserve instead of a simple load. And Brenda will receive the message back saying that the road is empty, just like Larissa did. So both of them have received the message that the road is empty, but both of them have read the semaphore with a load reserved. So now, what Larissa will do before going to the road, Larissa will attempt to do what's called a write conditional. Because she did a load reserve, she can now do a write conditional saying, if the value that is in that semaphore has not changed since the last time that I read, I want you to change that value to 1 and let me know that the write was successful. So she gets a response back saying, your write was okay. Nobody has changed the semaphore since the time that you read it. And now she has a confirmation that the road is actually empty. Brandon will try to do the same thing because Brandon also got the message initially that the road was empty, but Brandon also did a load reserve, so Brandon also gonna do a write conditional. And when Brandon tried to do a write conditional, what the write conditional is doing is saying, if the value of the semaphore has not changed yet, since the last time that I read, I want you to change it to 1, and I want you to tell me that you are successful. But of course, Brandon now gets a message back saying your write has failed, which means that someone else has changed the value of the semaphore before we are able to do your write. So you do not have the right to go into the road. So Brandon gets a message that the road is not empty. And then Larissa can go and cross through the road without any collision. So this better, and then once Larissa has crossed the road, she will be kind enough to write back to the semaphore and say, now I release the semaphore, I'm no longer interested in that part of the road. And at that point then, Brandon will be able to do another load reserve and will receive the message that now the road is empty, and will then be able to do the write conditional. Now the write conditional will succeed, and Brandon will be able to pass through the road, and everybody will be happy. There will be no collisions. So this is the enhanced synchronization that we need if you want to coordinate between the execution of multiple processors that are accessing the same memory. So, because the situation that we are contemplating where we have multiple RISC-V processors and they are all accessing the same memory, so how we coordinate the accesses? And of course, Brandon, after passing through the road, will write back saying, now I no longer need the semaphore. So we have two processors that are sharing an area of memory. And we have the situation where P1 writes and then P2 reads. So if P1 and P2 don't synchronize, the question is, what will P2 read? And in this case, P2 may read the value that was in memory before P1 wrote, or may read the value that is in memory after P1 wrote. So if there is no synchronization, it means that in the logic of my program, I do not have a need to synchronize, and I am happy. It is correct for P2 to either read the value prior to the write of P1 or after the write of P1. However, if P2 is supposed to only get the value after the write of P1, then I do need synchronization. So let's consider this example where I have, for example, the value 17 at the address 10100C in memory. And I have a processor P1. Processor P1 is storing a value into that address using S1, and processor P2 is loading a value from that address. So let's say that P1 is writing the value 42 to that address, and P2 is reading the value from that address. P2 may get 42. However, it may be that P2 does the read first. In this case, P2 gets 17, and after that, P1 writes 42. If I do not synchronize, it means that either of those values are okay with my program. So the result depends on the order of the access between the processors P1 and P2. Whenever I have a result that can depend on the order of access, like this one, I say that I have a data race. This is just a term used to indicate that the result of the read in P2 is unknown until the execution of the program. Here is a counter example, a counter update example. So in this case, what I have is that P1 is loading a value from memory, adding 1 to it, and storing the value to memory. And P2 is doing the same. So both of them are doing counter updates. The situation here is I have a function or a program that's executing P1, and I have a program that's executing P2. Maybe they are doing the same kind of tasks, and you need to count how many times you did that task. So every time that you do the task, you have to update a counter value. Let's say that the counter value right now is 17. And I could have a situation where P1 does the load first, so P1 gets the value of 17 from memory, and then P2 does the load and also gets the value 17 from memory. Now P1 adds 1 to that value and writes the new value to memory, so P1 will write the value 18, indicating that it has finished the computation of one more item, for example. And now P2 will also write the new value to memory, but P2 added 1 to 17 and also got 18. So I have a situation here where I had two counter updates, one by P1 and the other by P2, but the value of the counter in memory only got updated one time, or by one, because I have a data race between the access of that counter between P1 and P2. There are many applications where those data races are detrimental to the correctness of the program. An application, for example, where I cannot miss a counter. In that case, I need synchronization. With synchronization, I will ensure that the order in which the operations occur in memory is the same regardless of the execution of the program. So, in order to do synchronization, I must have hardware support. I cannot do synchronization only with software. So I need something that's called an atomic read-write memory operation. What that operation is an operation that will allow no other access to the location that I'm reading and writing in between the read and the write. So in the example of the counter, I want to be able to read the counter, update the counter, and write the counter back to memory, and in between, no other processor can do an operation to that memory location. So this is what atomic means, is that the read and the write are like an atom that cannot be broken apart. This instruction can be a single instruction, so I can have a single instruction that does the read and the write. And there are many different instructions that have been designed over the years to do that. So I have atomic swap of a register between a register and memory. So a single instruction will take a value from a register, put into the memory location indicated by the instruction, and take the value from the memory and put into the register. So I have a read and a write that occurs in a single instruction. Or I can have a pair of instructions. And this is what we're going to see in RISC-V. So just one more comment before we get to the pair of instructions. Certain architectures have multiple atomic operations, so I can do something like theta and increment, which means I issue a single instruction that will go to a memory position, read the value that's there, increment it by 1 or by a constant that I specify in the instruction, and put the new value into that memory position, for example. And there are many other of those instructions that I can have in some architectures. So here is how synchronization works in the case of the RISC-V. RISC-V has, just like I illustrated with my analogy with the road in the beginning of this lecture, RISC-V has an instruction called a load reserved, and the load reserved is an LR.W. W is for word, so is a load reserved word. It receives, has an address, and has a destination register. And then it has a start conditional. The start conditional also has a memory address, and it has two registers, two source registers and one destination register. So the start conditional is succeeds if the location has not changed since the load reserved word to that same location. And so the start conditional, different than a normal start, the start conditional returns a value. It returns 0 in the destination register if if it succeeds, and it fails if the location has changed. In this case, it returns a non-zero value into the destination register. Remember that the start instruction only has a source register and then the address of the memory. This start instruction has the source register, the address in the memory, and the destination register, that is where the result of the operation is returned. So one example that I can do with this operation is to do an atomic swap. An atomic swap is a test and set lock into a variable. What that means is that I can test a variable and set it at the same time. This is exactly what we did in the case of the road situation, where we wanted to be able to make sure that the semaphore is operated properly by reserving it with a single hardware operation. So let's do an example so that we understand exactly what's going on in here. And in this example, I have a processor 0. The processor 0 has in S1 the address of the shared memory location where I want to do the swap. And S4 has the local value, the value that P0 has to be swapped with memory. And then I have processor P1. The address of the shared variable in S1 in processor P1 is the same as in processor P0. They are both accessing the same memory location. And then in S4, P1 has a different local value than P0 has. That's the value that it wants to swap with memory. So this is used to do a test and set of a variable. So there is my shared memory location. So that box that I have in the middle is a single memory location. That's the memory location whose address is in S1 in both processor P0 and processor P1. So let's suppose that, for example, the address of the shared memory location is 0x1010 is 0, and the current value in that memory location is 42. And so processor P0 will have the address of that memory location. Let's say that the local value in P0 is 15 in S4. And P1 has the same address for the location because they are accessing the same location. But the local value for P1 is 37. So here's the code that I'm going to use to do this swap. First, I'm going to do in my try block, I will execute a load reserve instruction. So my load reserve is going to the address in S1, and the value that is loaded from that address is put into T0. So I will have both processors executing this code. So let's say processor P1 in its version of the code does the load reserve into that address and receives the value 42 back. It could have been processor P0 or P1 doing it first. The order should not matter for the outcome in this case. And what I have, the hardware support that I have here is that inside my processor P1, I have this load reserved address table, and processor P1 will enter the address of every instruction that every load reserve instruction that it executes. It's going to enter an address into that load reserve table to indicate that it has a valid load reserve operation into that location. Processor P0 will also execute a load reserved instruction. And in this case, processor P0 also gets the value 42 from memory. And it also enters in its load reserve table the address of the location that the load reserved where the load reserved has happened. So in this case, both of them have the same address in their load reserve table. They both have done a read and they both know the current value in the memory. So that in the case of the semaphore in the road would be the equivalent of when Larissa and Brandon got to both sides of the road and read the semaphore, and both of them in that case got the value 0 in their local places. So now the next instruction that both of processors will try to execute is the start conditional. So the start conditional will try to store a new value into that location, but will only do so if the location has not changed. So first, let's say that P0 happens to do the start conditional first. So what P0 will do is, if the location has not changed since the last time, then it will the start condition will succeed. In this case, so what the start condition will be doing actually is checking the internal table for load reserve addresses into P0. It will find that the address is there, is in the table, so it's okay to do the store. So the store will succeed. So the value that was the local value in P0, that was 15, will be written into the shared location, and the start conditional will return success. But something else happens. The way the synchronization works is that all the processors will be spying into the address bus and seeing all the operations that are happening there. So when processor 0 did the start conditional to write and was successful in writing the new value into that location, the processor P1 will hear about that conditional. How will processor P1 hear? It will be snooping into the bus. It will be looking into the bus, and it will be looking at all the addresses in the bus where writes are happening to. And by seeing that processor P0 was successful in doing a write to that location, processor P1 will going to look through its table of all its load reserve addresses and will remove the address that has just been written from its local load reserve table. So processor P0 is going to receive the result of the start condition operation. And when processor P1 tries to do the same thing, processor P1 doesn't even need to go to the memory, because processor P1 will check its own local load reserve table and see that the address is not there. So it knows that the operation has to fail. So notice that the start conditional word may not even go to the bus when it cannot succeed. So now we have the situation where the number 42 that was in the memory has been copied to processor P0. So there was a swap between 42 and 15 between P0 and the memory. So this will be the equivalent of Larissa doing the swap between the 0 and the 1 and being successful in reserving the location. Now I have a conditional. The conditional says, what was the result of my attempt? So what's the value of in T1? So processor P0 will check the value of T1 and see that's 0. So it has succeeded, so it can continue execution. But processor P1 has a value in T1 that's not 0. So processor P1 will gonna have to try again. So in the case of P0, the next instruction is to copy the value from T0 into S4. So it now has in S4 the value 42, and it has completed the exchange of values between the memory and the processor. Processor P1 will gonna go back to try again because it has a non-zero value into T1. So it will gonna start by doing a load read again. And it receives the value 15. It notes that in the case of the semaphore, it will be receiving the value 1 indicating that the other processor is still occupying the road. In this case, we don't have that code to check whether it's a 1 or a 0. We are simply wanting to do the swap, just to illustrate the swap. So it gets now the value 15 from the memory. And because it's a load reserve, it will write the address of that memory location in its internal load reserve table. And now we're gonna try to do the start conditional. In this situation, there has been no other operation to the memory, so it still has the address in its load reserve table. So it will be successful in completing the start conditional, because the address that it is trying to do the start conditional is in the internal load reserve table, and we'll be able to write the number 37 in memory, and we'll receive the value that the result that it succeeds. And now the branch will not be taken because T1 is 0. And now I'll copy the value from T0 into S4. And you can note that in this exchange, what has happened is that the value that was 37 that was in P0 end up, the value 15 that was in P0 end up into P1. 37 that was in P1 went to the memory, and the 42 that was in the memory went to the processor P0. So this illustration is not exactly like the semaphore that we illustrated in the beginning, but you can see that you can use exactly the same mechanism to implement the semaphore if I use the values 0 and 1s instead. And what will going to happen in the case of the semaphore is that then I go into a loop where I stay in the loop waiting until I read the value that is a non-zero value from the memory. So this is what I had for the load reserve start conditional instructions in the RISC-V architecture. And now I need to find how to stop my recording.